So in preparation for the exercise on hydrological analysis, let's just quickly go through hydrology, some basic hydrology, in case you're not familiar with this. Perhaps not read any geography beforehand, and we need to go through some basics. So here we are looking at a very simple map, a topographic map of a region, and these are the contour lines, elevation curves. So we have 30 meters above sea level, perhaps 40 meters, 50 meters, 60 meters, and these lines are constant. So this is all 50 meters here. We can see where the lines are close together, it's steep, and where they're more widely spaced apart, it's not as steep. The elevation change is much slower. And we can see that in these low points, the river is flowing here. So all the water runs downhill, and it will run at right angles to the contour lines, in theory. Downwards, and then at some point there's enough water for us to declare it a river. Another important feature to look for here is this dotted line that I've called here the watershed. What this means is that on the one side of this watershed, the water will run that direction. On the other side of it, it runs in the other direction. This line defines the catchment area, as it were, for this river. All the water falling within this side, on this side of the line, will flow into this river eventually, at some point. All the water flowing on that side will flow into a different river, or different rivers. So this tells us which areas are going to be contributing water to the river. All of these will not be contributing water to this river. All of this area will be. And we can see that in profile here. So we're now going to be moving over stepping towards a representation of this as a raster DEM. Here we have our watershed. Again, we're looking at this from the side now, but clearly the water runs downhill towards the river, and the water that's falling straight above falls into the river. But anything falling in here comes down into the river. Anything falling on this side of the watershed flows away from it, doesn't end up in the river. We can translate this then into our DEM. So the height of these columns here actually represents the cell value in our DEM. So we sliced through our DEMs when we're looking at it from the side. And then we say, okay, on each cell in our DEM, we're going to add a drop of water, or some amount of water. And in the simplest analysis, we're putting the same amount of water on each cell. Okay, so each cell receives 1 unit of water, rainwater. That will then flow somewhere. It will flow in a particular direction, determined by the slope and the aspect. It will flow downhill. So these ones we'll ignore for now because they're just flowing away. They're not part of our calculation. These ones are flowing away. We're going to ignore those. But when we start up here, the amount of water that this cell receives is 1. Stuff that came from straight up above. It then passes that 1 unit of water downhill. So this cell here has received 1 unit of water from above, plus the 1 from this cell up here that was sent to it. This cell has received 1 from above, plus the 2 that were sent to it from here. This cell has received 1 from above, plus the 3 that were sent from up here. This cell receives, and so on and so forth, when we go downhill. And then we can see down the bottom here, not only do we get an increase from this side, but we get an increasing amount of water coming downhill on this side, and they sum together to form 20. So we have the maximum amount of water accumulating here. And at some point we say, well, there's a river there, isn't there? We have to make a decision. We know that there was a river there. So what amount of water in a cell, accumulating in a cell, is equivalent to a river? And we'll say here 9, for example. Whatever that value might be, it can change. It will definitely change. But we make a decision. We say that if a cell has a value greater than 9, then it is a river. all of these have had water flowing over them, but not enough to make them rivers. They pass their water on down to here, and these will in turn pass their water on, but we can now call these rivers. And this is implemented in GIS. One method of implementing this is something called the D8 algorithm. There are 8 directions, and the water gets passed in one direction. We analyze which way is the steepest slope from a cell. So we're analyzing the central cell here, and if the water should flow off in that direction, well, this cell is going to get the value of 1. If it should flow off in this direction, it's going to get the value of 8. Here, the water is flowing from this cell in that direction, therefore this cell gets the value 8. So whatever value it had in the DEM, whatever its elevation was, is now irrelevant. We know that it's going to send its water in that direction. That cell sends its water in that direction, whatever its height was. We've got rid of that now. We're just looking at the direction it sends water. And in this case, number 8 is equivalent to sending the water down to the bottom right, sort of southeast. So let's just look at this. Let's do a little toy example. Here we have our mini elevation model, a mini DEM, and we have this, our D8 algorithm. So if it goes to the right, it's 1. If it goes to the top right, it's 2. Straight up, it's 3. North, it's 3, and so on. Another thing to remember is back to this thing with the distance and Pythagoras. The distance between the cells, if we go straight up, the distance from the middle point there to the middle point there is 1 cell. And likewise, straight over there is 1 cell. But what about diagonally? Well, then we have a slightly longer distance. We have 1.414 as our distance from middle to middle when going diagonally. That's important because we're interested in the slope. And slope is the change in elevation over distance. So the change in elevation here and here is one thing, but the change in elevation from there to there is another. Because of, well, it will be another anyway because of the, bad example, but because we have this greater distance for which the elevation changes over. So we can see that this is a very simple example because 10 there, 11, 11, that's up. And we're not flowing out of the elevation model. That's a kind of rule that we set. We always have to flow to where we know there's information, probably, unless it's steep, if it's higher all the way around, then we can flow out. But if there's a way for it to flow, it flows into the model. 9 is lower than 10, so it flows that way. So now we move on to the next pixel, 11. And that, looking around, well, 11 to 11, there's no change in elevation. That's higher, so it's going to go down there. 14, we've got a difference of 3 there, but that's an even bigger difference. So yeah, that's a no-brainer. It's going to flow down there. Difference of 5 down to there rather than a difference of 3. Well, this is where it starts to get interesting because the distance, because we've got a distance of 5, we've got an elevation change of 5 and an elevation change of 3. When we look at the slope here, 3 divided by that's 3 there and straight over. We don't need to worry about Pythagoras there. But on this distance here, 5, well, it's still greater than 3. 5 divided by the 1.414, it's still the slope is still greater than 3, still greater than going down there. So it goes over to 11. It could have gone down here, perhaps, potentially. If we hadn't done this calculation, we could have naively thought that perhaps that's not steep enough, but it is just. And we can continue analyzing the rest of the DEM like this to get the flow direction from each cell. And then at the end, it flows out. There's nowhere else for it to go, so it flows out. Okay. So now we can translate these into directions using this model up here. We get our directions. Okay, so that's our direction model. We know which way the water is going to be sent. Move on. There's our direction model. We then need to calculate accumulation. So we start here. That's not receiving anything. There's no arrow pointing into this cell. So it's only receiving water from above, 1. That's likewise not receiving any water from any other cell, just from above. All of these, this top row here, they're not receiving water from any other cell. Same with these. Now when we get to this point, we can see that, well, that has 3 other cells contributing water to it. That one, and that one all pour into this cell here. And it's got its own 1 coming from above, so it's got a value of 4. This one here is receiving water from that one up there, so that gets a value of 2. And then as we move down, we get to here, where this is receiving 1 from above, but it's also receiving 4 from here. It's receiving 1 from there. If you look there, it's receiving that 1 from there. It's also receiving that 1 from there, and it's receiving those 2 from there. So we end up with 9, summing up all the contributions from those cells around it that are sending their water to it. And then that sends its water on to there, which is also receiving water from there, and from there, and from there. So we get a total of 16 at this point, which is good. That's handy. That sums up to 16 because we have 16 cells. That's good. That means our calculation is correct. But that's not the end of the story, because we now know where we've got a maximum flow. We want a river, so we now have to set a condition. We say where we have a value greater than 3, say, for example, that is a river. So we code these cells as being river cells. Set the value of 3 just because I felt like it, because I wanted these cells to become our river. So that's greater than 3, that's greater than 3, that's greater than 3. These cells are the river. We can then combine these cells, say that one belongs to that one, and that one belongs to that one, turn that into a vector. There's a connection between them. So we've gone from topography and we've connected. We said that one and that one belong together. You can go from there to there, and you can go from there to there. There's a valid connection, and the value increases all the way. Is that topology? This is how the D8 algorithm will give you some streams. This is the analysis that you will do in the exercise.